So the title of my talk is a little misleading, okay? Cosmic Dawn and the Origin of Complexity. This talk is really about creation. So when we talk about creation, it's such a profound thing that we have a mental image of something that is so deep we don't actually understand it very well. And to a limited extent, that's true. So what we don't understand is why the universe was created. But what I find astonishing and surprising and just beautiful is that because of things that we've learned in the last few decades, we're at the stage now where we do understand a phenomenal amount about the process of creation, to the extent that aside from the tiniest fraction of a second after the Big Bang, we actually understand quite a lot about how the universe emerged at the time of the Big Bang. And part of the sad truth about why we know so much about how the universe emerged from the Big Bang is it's well-tested physics. And the reason it's well-tested is because of this equation, which is the only equation that I am going to show in this talk. Okay, and I don't feel I need to apologize for this equation because it's such a famous equation. It's almost an icon, right? You see it on people's T-shirts. But what this equation says, and this was first derived by Einstein in 1905, is that energy and mass are manifestations of the same thing. I can take a certain amount of mass and I can transform it into a certain amount of energy. I can take a certain amount of energy and transform it into a certain amount of mass. Now, the reason that we know that this is correct, that this process is actually true, is experimental. It's something that we test all the time. And it's sort of sad, okay? Because it's sort of a destructive equation. It's the equation that governs an atomic bomb explosion. And so, of course, when we look at E equals mc squared, it looks scary. But the point I'd like to make, okay, is that it's not a scary equation. It's an equation that doesn't just give you information about destruction, it also gives you information about creation. This is something that is broadly misunderstood. It's so misunderstood that it's actually even misquoted all the time, historically, by well-established historians who misquote J. Robert Oppenheimer, who was the father of the atomic bomb, who is said to have uttered upon witnessing the Trinity atomic bomb explosion in 1945 outside Alamogordo, New Mexico, as he saw that fireball rising into the air. He's misquoted as having said, "I've become death, destroyer of worlds." But that's not what Oppenheimer said. What Oppenheimer actually said was, "Now I am become Shiva, destroyer of worlds." Now, Oppenheimer was a well-read, educated guy, and he'd read the Bhagavad Gita. Okay, now in the Hindu philosophy, Shiva is a god that's associated with both destruction and creation, both aspects of that equation manifested in this Hindu god. Now, Shiva does indeed hearken the destruction of the cosmos, but the critical thing that Oppenheimer meant by saying this was that Shiva, upon bringing forth the destruction of the universe, sees the universe lying in ashes at his feet. And he does a dance. It's called the Nataraj dance. And the Nataraj dance brings forth a new cosmos that rises from the ashes. So what he meant really was that he was unleashing a force that was both destructive and creative. And it's actually the creative aspect of E equals mc squared that is most interesting. Okay, and it's this aspect of E equals mc squared that is actually most familiar to physicists. This is the Large Hadron Collider. This is actually just one experiment within the Large Hadron Collider. And the whole purpose of particle accelerators like this is to take a bunch of particles and speed them up to really high energy so that they're moving really fast, coming from this direction. And then a bunch of particles moving at really high speed with tons of energy moving in this direction. And then they smash together. And when they smash together, what emerges is energy from that collision. And from that energy, from that pulsing mass of energy, emerges particles that didn't exist before. Creation emerging from energy. That's exactly the process that occurred at the time of the Big Bang. So this is just a bubble chamber photograph of which there are literally millions. And what you're seeing here is the product of one of those explosions, when these particles crash into each other. And what you're seeing here is particles that did not exist before emerging out of nothingness. Particles and antiparticles. This is exactly the process that occurred in the tiny fraction of a second after the Big Bang. So we understand quite a lot about creation. It's not that mysterious. And so what we know about the time of creation at the moment of the Big Bang is that the Big Bang did this. The Big Bang made the stuff in these bottles. So it made hydrogen and helium. Okay? And that's it. That's it. The Big Bang made hydrogen and helium. But look around this room. How much of this room is made out of hydrogen and helium? Hydrogen and helium, the stuff in this bottle, these bottles, does not capture the essence, the beauty, the complexity, the richness of the universe. Frankly, I'm not interested in the stuff in these bottles very much. Really, what I'm interested in is the universe around us, filled with the good things, right? I want to understand how to go from the stuff in those bottles to lemurs and people and sunsets and chocolate and whiskey, the good things in life, right? And that's the key. That's the key, right? We want to understand how to go from simplicity, which is created at the time of the Big Bang, to complexity, the complex, rich universe we see around us. So it sounds like this would be a mystery too, okay? Because we talked about the first few moments after the Big Bang, and we saw that, it sounds like creation is going to be a complex thing, but, we know that the universe around us looks pretty complicated. So maybe this is the point at which things become complicated. But it turns out that's not true. We know how to go from the simple universe created by the Big Bang, the hydrogen and the helium, to the stuff on the right. We actually know that. And the key is stars. So stars are nothing but little machines that take the stuff in those bottles, the stuff created at the time of the Big Bang, and turn it into the periodic table, all of the other chemical elements in the universe. So I'm mostly made out of carbon. I'm breathing oxygen in this room. This thing is being held up by iron and other heavier elements. All these things emerge from stars. You emerge from a star. The atoms that are you were at one point inside a star. It's a phenomenal concept. And it's best encapsulated by words from my hero, Carl Sagan, who said, "You are star stuff." And he meant that literally. Okay, so the carbon that makes up the bulk of me was actually synthesized as part of the process that makes stars shine. The iron that holds this thing up was actually synthesized in a stellar explosion when a star died, okay, in a supernova explosion. So there are different ways in which stars make the different chemical elements, but they're done inside stars. So stars are really crucibles for the emergence of complexity from simplicity. Stars are the key. So knowing that stars are the key, you would now think that we understand, okay, how to go from the stuff in those bottles to the universe we see around us. But it turns out that there's actually a problem. So now is when we run into the problem. Now is where we, enter the regime of the mysterious, where we don't understand what's going on. And there are actually two problems. Well, there are many problems, but there are two big ones. So the first one is that we don't know how to make stars without the material created in the universe by previous generations of stars. What this is a nebula, okay? And this is basically a stellar nursery. Stars are being born inside of this thing. This cloud is basically made up of gas and dust. And the dust is a crucial component in making stars. We don't know how to make stars without that dust. But what's that dust made out of? It's made out of stuff like carbon and silicon. Well, where does the carbon and silicon come from? It comes from stars. So it sort of begs the important question of how do you then make the first stars? How do you make stars how do you make the first stars if you need stars in order to make other stars? How do you make the first stars? So this is a huge mystery, okay? And there's a sort of a cognitive trick that astronomers have adopted that I think goes to the root of knowledge, okay? And the cognitive trick is this, and it happens all the time in astrophysics and in astronomy because we're running up against these kind of profound mysteries in the universe. And the trick is this: whenever you run up against something that you don't understand at all, you just give it a name, and then you feel better. All right? You're no more clued in as to what is going on, but you give it a name. So what do astronomers do when they run up against evidence for these stars that somehow formed through some mysterious process from the pristine material in those bottles, a process utterly unlike that which forms stars we see today? We give it a name, and the name we give it is population 3. Okay, so when we refer to population 3 stars, we don't know what they are. We don't know the first thing about them, but we feel better because we've named them. All right? So that's the first thing. We need to come up with a way of forming population 3 stars. Nobody's ever seen one. Nobody knows how it could possibly work. We just kind of know logically it probably did happen. Okay, so that's the first problem. The second problem is a little more subtle, but no less fundamental. Okay, so the processes by which complexity emerges from simplicity are modulated by stars. But it isn't just single stars that are important. It's groups of stars. So the way this works is a star, which is, as I said, a little machine for making the chemical elements from the stuff in those bottles. The star will make those chemical elements as part of its shining and it's part of its eventual death. But when the star makes this stuff and gives it back into the universe, it just flings it out. And that stuff would not then be available to make next generations of stars which have some of those chemical elements in them. So what I'm saying is that the process by which complexity emerges from simplicity is part of a cycle of birth, death, and rebirth. Okay, stars are born, stars make all these chemical elements, eventually they die, they give up these chemical elements to the universe, and subsequent generations of stars form from that stuff, and the process continues. But if a star is alone, it basically dies, gives all of its stuff back to the universe, and subsequent generations of stars don't inherit it, right? They just form out of the stuff in that bottle again. So the answer is you have to form stars in groups. You have to not just form stars singly, but you have to form them in collections of many thousands of stars. And you have to collect those many thousands of stars into thousands of clusters of stars, and eventually bring them all together in this thing called a galaxy, which is comprised of billions of stars. And the galaxy has so much gravity that it can hold all this stuff together. Okay? And holding all this stuff together is the key to allowing subsequent generations of stuff to get more and more complicated. But the problem is you cannot build a galaxy out of the stuff in that bottle. The stuff in that bottle will collapse on a time scale and on a size scale that is completely wrong. It doesn't describe any galaxy we see out there. So somehow the stuff in that bottle doesn't seem to work in terms of explaining galaxies. So what's the answer? The answer is actually known. You do something to the stuff in that bottle to make it work. And so to explain this to you, I have to make a confession. And the confession is that I was lied to, okay? And I think you were probably lied to as well. And I was lied to in kindergarten, all right? So in kindergarten, I don't know about you guys, but in kindergarten, I was told this, okay? Everything is a solid or a liquid or a gas. So hands up everybody who was basically taught this, right? Just about everybody, right? Wrong. All right, so what's phenomenal is you know who got it right? The people who got it right were walking around in togas 2,000 years ago. The people who got it right were the ancient Greeks. Okay, so the ancient Greeks said, no, matter is made up of earth, air, fire, and water. All right, so water is a liquid, earth is a solid, air is a gas. But what's fire? Right? What is fire? Well, fire actually turns out to be a state of matter entirely on a par with solids, liquids, and gases, and it gets a name. So the name it gets is a plasma. So I'm going to now do a scientific experiment that you should not participate in if you have H1N1. Otherwise, it's audience participation time. Okay? So you all think you're people, but for the purposes of the next 3 minutes, you're actually atoms. Okay, you're all atoms, and now we're going to be a solid. All right, so this is, you're going to have to turn around to the person sitting next to you and make friends. Okay, if you don't know them, introduce yourself. So we're going to be atoms. So Chris, could I borrow you for a moment?
Yeah.
Okay, so hold hands with the person standing next to you. Okay, so this is a great way of making friends. All right? Okay, so you're an atom, and now you're gripping tightly, right? So what you are now is you are a solid. All right, so basically a solid is a collection of atoms held together with a tight bond. Now, we hold sort of like, feetly, kind of gently, not really properly holding at all. Like you don't know that person or like them very much. All right, so now you're a liquid, okay? And a liquid is basically atoms that are held together kind of loosely. Okay, so for the next one, Chris, thank you. We don't need you now. Okay, so for the next one, if you, and we're just going to do this one mentally, okay, because it would be chaos if we tried doing it any other way. So for a gas, if you stood up and you just sort of walked around the room, and whenever you bump into something, you kind of randomly scoot off, and then you hit each other, and then you just bounce off of each other, then you're a gas. And the illustration of a plasma is my own special invention, which is probably the most useful pedagogical thing I've ever come up with. But it will also get me arrested if you actually did it. Okay, so just imagine it. Okay, so here's what a plasma is. Imagine you stood up and you removed all of your clothes, okay, and then naked you ran around bumping into each other, and your clothes, independently of you, ran around bumping into each other and all of the other clothes. That's a plasma. Okay, so what a plasma is it's a collection of atoms behaving kind of like a gas, but the outer layers of those atoms have been stripped off, okay? And those outer layers of those atoms are behaving independently of what's happening with the center of the atom. So that's what a plasma is. And it turns out that the properties of a plasma are actually very different from the properties of gas. So the key property of a plasma that's of relevance here is that a plasma will collapse on the right size scale over the right time scale to make something that looks like a galaxy. So how do you make a plasma? It's easy. All you do is you take the stuff in that bottle and you blast it with energy. All right? So the picture of a fire is a very apropos picture. Right? You take a gas and you blast it with energy, and then you turn it into this plasma thing. And it turns out then that if you want to make a galaxy early in the universe, you have to take our universe and blast it with energy. And that is, in fact, what happened. Okay, so there are all of these measurements that people have made, and we now know that the universe today is mostly comprised of stuff in that bottle that has been blasted with energy, so that the stuff in that bottle is now a plasma. But how and why? The Big Bang was this phenomenally energetic process. Okay, so you can understand why, the universe being born in fire would be very energetic. But why would the universe exist as a stuff in that bottle, and then later on something come along and nail it with energy? It's a mystery. So that mystery is encapsulated. I lied. This is another equation, but it's not a real equation, okay? So I said I would only show one, and apparently I'm showing two. All right? This is another equation, and this is the idea, all right? So the idea is you take the stuff in that bottle created at the time of the Big Bang, okay, created by the Big Bang, and then you add something to it, and then what you wind up with is a plasma. So what do you do if you're an astronomer and you don't understand what's going on? Give it a name. And then you feel better, right? So we have given this a name. Okay, astronomers give this a name. We call this thing first light. So what we refer to by first light is simply a process by which the stuff in this bottle gets nailed with a vast amount of energy, and the universe becomes a plasma. So first light is the holy grail of observational cosmology. If you are, like me, a guy who works mostly on the early universe, the formation of galaxies, this is the sexiest problem to be working on. This is the problem which you wake up in the morning and you sit in front of your computer and you anxiously look to see the latest news on this problem. This is the problem for which you try and hire people to make your department look better because they work on this problem. This is the problem for which you spend billions of dollars to build space telescopes in order to tackle. This really is the hugest thing right now in terms of observational cosmology. So since this is the holy grail of cosmology, it means that astronomers, okay, are on a grail quest. right? So that's really our mission, right, is to get at first light. And if astronomers are on a Grail quest, that's me, kind of the dumpy python with a silly mustache. Okay, so let's recap the big idea. Okay, so the big idea is that the universe is created, and the universe was created 13.7 billion years ago. And that is, phenomenal that I can tell you that with some precision. I can tell you that number to within about 5%. And that's big news, okay? That's really, the ability to give you that number with that kind of precision is only a few years old. Okay, so 13.7 billion years ago, the universe was created. Now, sometime after the universe was created, some other process occurred that dumped a ton of energy into the universe and turned it from a neutral gas, the stuff in that bottle, into this plasma. That change allowed the formation of galaxies and stars to occur, and thus that change, that first light event, is essentially the catalyst for complexity. The complex universe you see around you emerged because of whatever caused the universe to become a plasma. Whatever dumped all that energy into the universe is kind of the starting gun on the road to complexity. And we call this starting gun, this starting point, first light, because we don't have a clue as to what it is. So I can't tell you what first light is. I can give you some alternatives, okay? So some of the alternatives are stars that are 1,000 times more massive than the most massive stars that exist today, that formed through some process utterly unlike any stars that form at present. Okay, so that's one thing that people at the University of Toronto who do theoretical astrophysics sit in front of their computers and think that they can maybe understand how to form the first stars if they make them supermassive. Now, these supermassive stars give off tons of radiation, and when they die in these colossal explosions that are so energetic that they utterly dwarf any conventional supernova explosion. That's one alternative. Another alternative is that the Big Bang, in addition to forming the stuff in that bottle, also formed a ton of black holes. And those black holes begin to suck matter in sometime after the Big Bang. And as that matter swells into the black holes, it gives off energy. And that energy is responsible for this. Another alternative is that there's this mysterious substance called dark matter out there. The entire subject of a different talk, okay, is that everything that you see in the universe is only a tiny fraction of what's really out there. The reality that you perceive with your eyes is only 3% of the universe. 97% of the universe is made up of material that you cannot see. The only way you can feel it is through the effects of gravity. So this is stuff called dark matter or dark energy. And it's possible that dark matter is made up of particles that decay. And when they decay, they give off tons of energy that set us on this road to complexity. That's another alternative. Another alternative is that we have no clue at all. It's none of the above. It's some mysterious physics that we just have no idea about. And I would actually plug for option number 4, all right? Just because that's kind of the way, the perversity of things, right? Usually it's something you haven't thought of. So we don't know what first light is, right? But, and this is phenomenal progress, I can stand up in front of you and I can at least tell you when it occurred. And this is new, okay? I couldn't, if I had been here 5 years ago, I couldn't have done this. But I can tell you now that first light occurred 800 million years after the Big Bang. Almost a billion years after the Big Bang. Call it a billion years. So in your head, here's what you should have a picture of. The universe is created 13.7 billion years ago. The universe exists like that stuff in the bottle. A billion years later, something occurs, okay? That something somehow occurred, and the universe fundamentally changed. We don't know what it is, but we at least know when it happened, and that's new. So how are we going to find it, right? This is obviously the Holy Grail. How do we figure out what caused first light? Well, I'll tell you, there are a bunch of options, and people are working furiously upon this problem. And I can't tell you the mechanism that's going to work, but I will present some options, and brace yourself now because those options are all expensive, all right? So option number 1, weird stars blowing up. There's a satellite up there right now called SWIFT that costs $300 million, and SWIFT is able to detect these enormous explosions called gamma ray bursts incredibly far away. So if first light is being made up of these supermassive stars in huge abundance, then SWIFT ought to be able to pick them up more or less now. The best option is to use this magnificent telescope, which is the successor to the Hubble Space Telescope called the James Webb Space Telescope, that I am proud to be involved in, and which is only possible through generous donations of taxpayers such as yourself, because Canada is involved in this project. It's a $6 billion project in which Canada is a participant. We built important aspects of this telescope, and it's going to be launched in about 5 years. And if you can't tell, I'm pretty darn excited about this thing. Right? The next 5 years are torture for me, just waiting for this thing to launch. So that's, in my opinion, the best option. But there's a third option, sort of a skunk works option that I hope works out, because then I'll be on the next jet to Stockholm to cash my check. All right. And so this is an option that I'm concocting using, well, I'll explain the experiment in a little while, but it's using the Gemini telescope and some fancy technology, part of which is being developed at the University of Toronto. And we ought to know if this works next year. So I'll focus on this a little bit as well. So I can now do this. All right, I couldn't do this 2 years ago, but I can now tell you that people have been looking hard to see whether or not these colossal explosions in the very distant universe have been occurring, and they have been seen, but very, very rarely. Okay, not nearly enough of these huge explosions to explain first light. So I can now draw a bar through this thing and say it isn't anything that was detected by the satellite. So the best options are these two, and so those are the ones we're going to focus on. So the James Webb Space Telescope, the successor to the Hubble, looks totally unlike the Hubble Space Telescope, which is now, so iconic. You all have a picture of it in your head. This is not at all like the Hubble Space Telescope. The James Webb Space Telescope is much bigger. It has a different purpose, okay? Rather than looking mostly at the light that your eyes are sensitive to, it's actually sensitive mostly to radiation that has a longer wavelength, the sort of infrared radiation. It looks at the sort of radiation that, those police heat cameras when they're looking at miscreants from helicopters. That's basically the radiation that the James Webb Space Telescope is looking at. So it's enormous. This is a full-scale mock-up in front of the Northrop Grumman Space Technologies building where it's being constructed. And it is different from the Hubble Space Telescope in many ways. The Hubble Space Telescope was launched about 20 years ago, placed into near-Earth orbit, so it only orbits a couple hundred miles up above the Earth. The James Webb Space Telescope is completely different. Okay? Rather than orbiting around the Earth, it's actually being launched so that it orbits out by the moon. Okay? So the idea is it is in a location where it can be pointed away from the sun at all times. And the idea there is that it has to cool to only 30 degrees above absolute zero. So it has to be kept very, very cold because it looks for this infrared radiation, which is heat. So you have to cool it down. And it's so big, it cannot be launched in one piece. So the Hubble Space Telescope was launched in one piece inside the bay of a space shuttle. This thing is too big for that. So instead it's launched, folded up, and then it unfolds, kind of like an accordion. It's magnificent technology, but it's also super risky. Okay, so as far as I am aware of, okay, there's been nothing like this constructed ever. That said, there are things apparently that I am not aware of that the US Department of Defense apparently has constructed that look similar to this. Okay, so that's, so the reason I can't tell you how Jesuitical I have to be with this, because I'm on certain committees that, look into the probability that this thing is actually going to work, right? And so there apparently might be, we're told, things out there that look similar to this, that give us some confidence that it's going to work. Okay, anyway, I don't want to wind up in Guantanamo Bay. All right, so the James Webb Space Telescope, how does it compare to the Hubble Space Telescope? Well, now I have to tell you about the astronomer's big trick. It's beautiful to be an astronomer. I love being an astronomer, and I especially love being an astronomer when I talk to other scientists, because I can do this. Ha 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 ha. I have a big trick that you don't have. Okay, so now I'm going to tell you the big trick. Okay, the big trick is that if you're an astronomer, you can look back in time, right? And the reason you can do this is because telescopes are time machines. So you didn't know that probably, or you hadn't. Some of you probably did. Okay, telescopes are time machines. What do I mean by this? What I mean by this is if you go out and you look at the sun, you are not seeing the sun the way it is now. You are seeing the sun the way it was 8 minutes ago. If you go out and you look at the nearest star, you are not looking at the nearest star the way it is now. You're looking at the nearest star the way it was 4.3 years ago. Because it took light 4.3 years to get from that star to your eye. It took light 8 minutes to get from the sun to your eye. Light moves incredibly fast, 300,000 kilometers a second. But fast as that is a finite speed. It takes time for light to go from A to B. Okay? So if I look at one of the nearest galaxies, the Andromeda galaxy, I am not seeing the Andromeda galaxy the way it is today. I am seeing the Andromeda galaxy the way it was 2.3 million years ago. So I'm looking back in time. So note the trick. Okay? The trick is, if I want to look back in time, all I need to do is look at something far away. And if I want to look further back in time, I just look at things further away, right? So that's the astronomer's big trick. If I want to see something as it was 10 billion years ago, all I need to do is look at something 10 billion light years away, because it took light 10 billion years to get to me. So I can look at stuff back in time. Now let's think about what the implications are. If I wanted to, if I could come up with a technology, I could look to a time when first light occurred. Remember, I told you when first light occurred. We now know that. It occurred 800 million years after the Big Bang. The Big Bang was 13.7 billion years ago. So if I can look 12.9 billion years back into the past, I can see first light occurring before my eyes. And that's the beautiful thing about being an astronomer. Imagine you're an archaeologist. You just have to, look at the fossils. If you're a paleontologist, look at the fossils. If you're an astronomer, you just look out and you can see those dinosaurs walking around. Okay? So it's a beautiful trick. You can use telescopes as a time machine. This is the Hubble Deep Field North. This was a transformative observation made by the Hubble Space Telescope a little over 10 years ago now, okay, which at the time represented humanity's deepest look out into space and thus humanity's deepest look back into time. This observation changed my life, okay? The day after this observation came out, I looked at this thing and I knew so much more about galaxies, it was just like taking textbooks and ripping them up, okay? This one observation utterly transformed our view of how galaxies form. Now, the amazing thing about this is that almost everything you see here is a galaxy. There are only like 4 stars in this thing. What the Hubble Space Telescope did is it pointed at a tiny, tiny patch of sky for a week. And it opened its shutter and just collected all the light for a week. So this is a phenomenal observation. If you look at these tiny little galaxies and you ask how far away they are, it turns out that they are about 9 billion light years away. So I'm seeing these things as they were 9 billion years ago. I'm seeing these things as they were about 5 billion years before our sun even formed. Okay, so a phenomenal observation, but not good enough. Remember, if we want to use this observation to understand first light, we need to go back 12.9 billion years. With the Hubble, we're only able to go back 8 or 9 billion years. The Hubble is not big enough. The Hubble won't let us understand first light. This is a simulated observation with the James Webb Space Telescope, okay, which hasn't been launched. So, this is, somebody has plugged into a computer what they think, the James Webb Space Telescope will see. When plugged into this computer, what these people assumed was that first light was made up of these massive stars collected together in early galaxies. They put these early galaxies, 12.9 billion years into the past, and we can see them peppering this image. So the James Webb Space Telescope ought to do the job, okay? To compare it with the Hubble Deep Field observations, the Hubble Deep Field is shown at the top, and the simulation of the James Webb Space Telescope observation is shown at the bottom, okay? So this is why I want to, cryo-freeze myself for the next 5 years and get thawed out, all right? Because I'm so excited that we are on the cusp of actually being able to at last understand the origin of complexity by finding the first galaxies with the James Webb Space Telescope. But that would mean waiting 5 years. I can't wait 5 years. Nah, I'm going crazy now. I'm not a patient person. 5 years will kill me. Okay, so I've spent the last few years trying to come up with an alternative strategy to try and get there sooner before the James Webb Space Telescope, which I'd now like to try and describe. So this is basically all about cheating, okay? Because the James Webb Space Telescope is the way to do this thing, all right? But I don't want to wait 5 years. I want to cheat and get there today, all right? So in order to get this to work, or maybe to work, you have to cheat like crazy. Okay, so cheat number one. Yeah, not one cheat, you need 3, okay? Cheat number 1 is you rely on nature to make your telescope bigger than it really is. So it turns out that in Einstein's theory of general relativity, okay, matter bends light. So what's a lens? A lens is basically a material that bends light. So what that means is that if you can find enough matter, a big collection of mass plunked into the universe, you can use that as basically a lens, all right? And so this is called a gravitational lens, and it's a trick because a lens amplifies light. It lets you see things appear to be much brighter. So there are these huge collections of mass out there called clusters of galaxies, collections of many thousands of very massive galaxies, and if you look through them, you can use those clusters as lenses to amplify things seen behind them. Here's an example. The 2 little splodges there, marked A and B, are actually very, very distant galaxies that are seen about 10 times brighter than they really are because they're being amplified because this line here, well, I won't explain the details, but they're being amplified by the foreground cluster of galaxies, and they appear 10 times brighter than they really are. That's cheat number 1. So, cheat number 1 will actually land you on the cover of Time magazine because Richard Ellis, who's kind of my mentor, okay, claimed a few years ago to have found a number of objects far enough away to be candidates for being first light. This is utterly unconfirmed. Okay, so 1 cheat is not going to do the job. So what's the next cheat? So the next cheat is beautiful because I get to wave the flag. Okay, so Canada is constructing important bits of the James Webb Space Telescope. This is an engineering model of the James Webb Space Telescope, and everything that's shown in color here is being made in Canada, designed and made in Canada. It's magnificent high technology. Now, the bit that's of most interest is this bit here, okay? So this is basically 2 very, very precisely manufactured pieces of glass that when squished together allow light only of a particular wavelength to pass through it. It's called a Fabry-Perot-Edelon, and it's the heart of the instrument that Canada is building for the James Webb Space Telescope, and that instrument is called the Tunable Filter Imager. It's a magnificent achievement. But rather than just wait, okay, I thought, if it's such a magnificent achievement, maybe I can steal this magnificent achievement and use it without waiting 5 years. So the question I asked myself when this money magnificently dropped from the sky when I won this prize was, can I use this money to steal this technology and use it early? And the answer is, I hope yes. Okay, so this device is sitting in the basement of the astrophysics building at the University of Toronto. It's called F2T2 for obscure reasons which I won't bore you with, but it is hunks of glass, very precisely manufactured, squished together. This is an engineering prototype of the device that's going to be flying on the James Webb Space Telescope in a few years. And that is cheat number 2. The way cheat number 2 works, okay, is intended to isolate a particular wavelength at which most models for sources of first light say these sources of first light will give off like half of their radiation in just this one wavelength. So the idea is to just pick that one wavelength out, and you should be able to see things that are much fainter than you could otherwise detect them. So that's the essence of cheat number 2, but that's not good enough. Cheat number 2, not good enough. We need cheat number 3. So we need cheats 1, 2, and 3 in order to make this work. Cheat number 3 relies on some exciting technological developments that seem set to revolutionize how we do astronomy from the ground. This is the Gemini telescope. It's the source of this cheat, but this cheat is now being used on many other telescopes. So the problem, okay, is that when you look at stuff in the universe from telescopes on the ground, things look blurry. And the reason things look blurry is because of Earth's life-giving atmosphere, which is screwing up our astronomical observations. Okay, and so that really is best manifested by twinkling of starlight. Okay, the twinkling of starlight, when you look at it, is basically Earth's atmosphere messing up astronomy. So when my 5-year-old came home from kindergarten, and he said, Daddy, I learned twinkle, twinkle, little star, how I wonder what you... I'm like, stop! Daddy hates twinkling. No singing that horrible song in this house. Okay, so twinkling of starlight is the enemy, okay? We have to come up with an anti-twinkling device, which means that you ought to be able to use a telescope from Earth and see images with the clarity of the Hubble Space Telescope from space. So the anti-twinkling device is something called adaptive optics. And adaptive optics has been, a panacea that people have been working on for about 20 years, and it's really only with the development of a new technique for doing adaptive optics using lasers that this technique seems ready to take the final step to being something really useful. So let me describe how this works. And this is the Gemini North Telescope's adaptive optics system animated. Okay, so this shows it working perfectly, and it's actually a technology that works, in my experience, like half the time, right? So this is kind of the best case scenario. So a laser, a very powerful laser, is launched into the atmosphere, and it hits a layer of sodium atoms about 90 kilometers up. Those sodium atoms are placed there by meteorites, which burn up in Earth's atmosphere and leave a layer. So when you illuminate that layer from the ground, what you see is a very bright star, which you can place anywhere you want, okay? So the light from that very bright star is the key to doing the anti-twinkling, okay? Because what you want to do is take the light from that very bright star and you want to input the reverse of that twinkling into your computer. So you take out the twinkling by figuring out how the twinkles are occurring, putting the negative of each twinkle into your telescope, and then taking it out. So the way this works is using this fancy mirror here, which is called a deformable mirror. And so it almost has a surface that looks like a liquid, okay? And so your computer can control this mirror and it can distort it, okay? It looks like the surface of water on a pond. And it takes these distorted wavefronts and turns them into these nice, beautiful wavefronts and takes out the twinkling. Okay, so this technique, when it works, is awesome. Let me show you some examples. This is Jupiter's moon Io, shown on the far right, as seen by the Voyager 2 spacecraft, which is just zipping by Jupiter and just taking some pictures. The image on the middle is Jupiter's moon Io, as seen by the Keck telescope's adaptive optics system, and the image on the far left is what you would get without adaptive optics. So you can see that you can use a telescope on Earth, look at this moon of Jupiter, and see something that looks almost as good as if you were a spacecraft right by Jupiter. So it's astonishing. Here is Neptune, again seen with the Keck telescope's adaptive optics system, and as seen without the adaptive optics system. So it's a magnificent technology that seems set to do this, and this is now a simulation. So this is a galaxy seen without adaptive optics. This is the same galaxy seen with adaptive optics. So you're now seeing this galaxy with the clarity of the Hubble Space Telescope, but you're seeing it from Earth. So it's the combination of these three things that we hope will, next year give us the opportunity to look for the sources of first light 5 years ahead of the James Webb Space Telescope and hopefully land me on that plane to Stockholm. Okay, so what are we going to find? Okay, so I have a strategy, okay, for when I want to understand what one of my observations is gonna do for me. So I go to the 14th floor of the astrophysics building at the University of Toronto, where there's a place called the Canadian Institute for Theoretical Astrophysics, where a collection of some of the biggest brains on the planet sit down and think hard about the universe. And they go to these guys and say, hey, Fred or Joe, I'm doing this. I'm going to look with this telescope. I'm going to try and do this thing. What do you think I'm going to find? And then I ask them, and Fred or Joe will confidently tell me what I'm going to find. And then I walk out of there happy, because I know that whatever I find, it's not going to be anything that Fred or Joe have predicted, right? So it's a fantastic, almost unbroken streak, okay, of failed predictions. So I'm not going to show you what Fred or Joe are predicting I'm going to find, okay? And I do this with the assurance that whatever we find, it's not going to be this. But here's what they say I'm supposed to find, okay? So this is a hydrodynamical simulation showing the formation of supermassive population 3 first stars 800 million years after the Big Bang. So there's this cloud of partially ionized or partially plasma and partially the stuff in the bottle, hydrogen. And at the very heart of it, there is a supermassive star. This star, as I said earlier, is about 1,000 times more massive than any star in the present universe. It's so massive, it's as massive as almost a globular cluster of stars. It only lasts a very short period of time, measured in hundreds or thousands of years. And when it dies in a colossal explosion that is thousands of times more luminous than any supernova. And it leaves relic radiation that is moving off at some fraction of the speed of light. So that's what is predicted, okay? But the real thing that I expect to find is mysterious. I have no idea what we're going to find, okay? We're just using the trick, okay? And the trick is we just go out there, we look far enough away that we can look at the time where first light occurred, and we have a very humble viewpoint, okay? We just are going to look at the universe and see what it tells us. And I expect to be surprised, okay? And the reason I expect to be surprised is I have now been doing astronomy professionally for over 20 years, and what I have found is that the universe is vastly more interesting and rich and surprising and mysterious than the human mind can comprehend. So I would like to now illustrate this by showing you some new results that just emerged, that just hit the presses, as it were, a couple of weeks ago. And these new results were obtained in an area completely separate from first light, yet emerged from our analysis of first light, preparation for first light, by the student who built those very precise pieces of glass. Okay, so she, her name is Erin Mentuk, and she's now famous, okay? There are hundreds of articles and newspapers have emerged from this stuff a couple of weeks ago. And I'd just like to describe her observations. And well, let me just first set the stage for these observations. So Erin is in the final year of her PhD. Now, her PhD plan was to use those two pieces of glass with Gemini telescope and try and find these sources of first light. When we concocted this plan, this was a number of years ago. Now, Erin would like to graduate sometime before the end of the universe. Okay, so what's happened in the meantime is that the technology that we need in order to implement this plan, trick number 3, this fancy adaptive optics thing, is late. Okay, so about a year ago, Erin and I sat down and we said, Erin, we have to come up with a plan if you want to graduate on time, because plan A is not going to work unless you want to stick around forever. We need a plan B. And so Erin basically said, well, Bob, I have developed all of these tools for looking for first light. Maybe we can come up with something else to do interesting using these tools. And I said, okay, Erin, I have this boring data sitting on disk, which I obtained a few years ago, and I looked at it and nothing really exciting was on it. So you take a look at it and see if you can come up with something interesting to do with it by applying these tools that you've developed for our first light machine. So Erin did exactly that. Okay, so this data is from a survey called the Gemini Deep Survey. We obtained the data for this 6 years ago. We've written 11 papers on it, and so I thought it had been mined out. Okay, but I thought enough was left there so that Erin could get her PhD thesis out of it. So I'm not going to describe this in gruesome detail, but I just want to show you one plot which illustrates what she found. Okay, so along this x-axis here is wavelength, and along the y-axis, the vertical direction, is the intensity of light. All of these little dots correspond to light from a galaxy. All right, so these are all galaxies, and we're studying their properties of their light as a function of wavelength. The solid and dashed lines here correspond to models. Okay, so we think we know a thing or two about how to model starlight. We think we know a thing or two how to model dust in galaxies, which is what dominates the light over here. So stars are over here, dust is over here. Now, Erin used all of these models, again, developed for this first light experiment, and found that there was always an excess of light over here in this gray band. There was nothing you could do to these models that would explain this excess of light. And we were astonished, okay, because we tried everything. We tried different models, different assumptions, everything you can imagine. Nothing worked. So ultimately we said, okay, galaxies are made up of stars and dust. So what could it be that we're missing? What extra thing could be in galaxies that would basically be giving off light right here that isn't in our models? So we thought incredibly hard about this and eventually came up with the answer, okay? And the answer is these things. These are called circumstellar disks, and what they are solar systems in the process of forming. So when you make a star, 99% of that gas goes to making a star, but 1% of it is left over. That 1%, which is left over, collapses into a disk, and that disk is rotating, and that stuff eventually then collapses and forms planets. Okay, so these things are proto-solar systems caught in formation. In 1 million years or so, this is going to be a collection of planets. So it turns out that these things radiate in exactly the right way and are predicted to be in exactly the right numbers to explain what Aaron found. So what Aaron found was thousands of solar systems in formation in galaxies being seen in the very distant universe. This Gemini Deep Deep survey is focusing on galaxies that are being seen 6 to 8 billion years ago. So what Aaron discovered was solar systems, planets being formed in these galaxies billions of years before our sun even formed. A magnificent discovery. First time anybody had found anything like this. One of the most exciting areas of astronomy these days is the search for these things called extrasolar planets, planets outside our solar system. Aaron knocked this so far out of the park, they're not even outside of our solar system. These planets are even outside of our galaxy. They're not even in nearby galaxies. These are incredibly distant galaxies. So she is able, using these observations, to say stuff about the formation rate of planets, not just nearby, but in the very distant universe. She's able to say stuff about the formation rate of planets as a function of the history of the universe itself. So a magnificent discovery, I think, that I had very little to do with. And what was interesting about it was once we went down this road and started thinking about it, all sorts of connections emerged, including connections to ourselves. Okay, so we talk about how to go from the stuff in that bottle to the complex and rich universe we see around us. But really, a lot of that is trying to understand ourselves. Okay, I guess it's a human need to try and turn the focus upon yourself. And so we were able to look at the formation of things in our own solar system and ask whether at some point the protostellar nebula in our own solar system resembled the sorts of things that Aaron was seeing in these observations. And it turned out that there was a paper by a different Abraham, this is not me, that appeared in Nature, okay, at the same time as we were doing our stuff on the very distant universe that looked at the formation of our own solar system and our own planets. And what was found, okay, using data from a space probe that collected dust from the tail of a comet, was that the tail of a comet, if you look at the material in it, contains dust that has these little particles in it that are crystalline. And those crystals formed through an annealing process where our proto-solar nebula was heated up to 1,000 degrees and allowed to cool. Exactly the sort of thing that she was seeing in these very distant objects. So astonishing how we went, okay, from studying first light, the origin of complexity, and somehow, by accident, without even intending to do it, wound up studying the tails of comets and the formation of our own solar system. So our initial idea was to study the event that set in motion this chain of events leading to complexity, and by accident, we wound up studying that complexity itself. And we didn't predict it, okay? And that is, I think, the lesson, in some ways, of astronomy for the last 400 years. This is the Galileo lecture series, and this is another trick, okay? Astronomers are simple people. We only have a few tricks, okay? Trick number one is if you want to study a phenomenon in nature, you watch it happen before your eyes by looking back in time and seeing it occur. Trick number two is if you want to make a magnificent discovery, you just build a bigger telescope, okay? It's the trick that worked for Galileo. Every time we build a new generation of big telescopes, magnificent discoveries seem to emerge. And it's like a perfect correlation. You know, when we built the 100-inch telescope, we discovered, or not we, Hubble discovered the expansion of the universe. When the 200-inch telescope was built, then quasars were discovered, these vast beacons of energy that allowed us to probe the universe at incredibly distant horizons. When the Hubble Space Telescope was built, this dark energy was discovered, this constituent of the universe that dominates everything that we hitherto had not even suspected existed. So all we need to do in future to keep this chain of events going is to keep building bigger telescopes and then sit back and gaze in wonder as the universe surprises us. Because the universe, as it did here, surprised us. So this observation that Aaron made, it turns out, united all of the science goals of the James Webb Space Telescope. If you go to the website for the James Webb Space Telescope, you'll see that its mission is to find planets, to study the formation of stars, to study the formation of galaxies, and to look for first light. In that one observation, entirely by accident, entirely by surprise, all of these things were looked at the University of Toronto with your taxpayer dollars, for which I thank you. And I'll stop there.